online Solvay Colloquium by Professor Pavel Kovtun from the University of Victoria. And the title of the colloquium is Hydrodynamics Beyond Hydrodynamics. So before I give the floor to Pavel, let me say a few words about online Solvay. Hello? Someone spoke. So maybe all the mics should be off except Pavel's and mine. So Pavel got his PhD at the University of Washington and then moved on a postdoctoral position to Santa Barbara from 2004 to 2007. And in 2007, he moved to the University of Victoria, where he's now a professor. He is one of the pioneers in the application of holography to hydrodynamics and to that general field. So it's a great pleasure to have him today for a colloquium. Well, we have him virtually, but I hope that at some point we will be able to extend to you a more physical invitation. So Pavel, the floor is yours. Thank you.
Thank you. Thank you, Mark, for the kind invitation, for the opportunity to come even virtually and share some of my ideas. I should say, please feel free to interrupt me at any time, or if the current practice is to wait till after the talk, that's fine as well. And also, if I somehow forget myself and try to go over time, also please make it known to me. Okay. So hydrodynamics beyond hydrodynamics. What do I mean? So I'm a little bit even afraid to talk about this. It's such an established field with a long history and many applications. But I don't want to talk about applications. I want to highlight some foundational questions that came to light in the last few years. So my own background is in field theory, theoretical physics. So slightly more precise title is a theoretical physicist perspective on hydrodynamics, and you will see what I mean when I proceed to talk. So what is hydrodynamics, first of all? It's basically a set of equations that tell you how stuff flows. So what is stuff? Stuff can be water, air, can be a cold atomic cloud or hot primordial matter in early universe, can be electron fluid in a solid, whatnot. And I remember myself being a student studying hydrodynamics. So as a student, you open a book that says hydrodynamics or fluid dynamics on the cover, and you often see derivations, approximations, applications, and everything will be sort of mixed together. And if as a student, you're also learning about vector calculus and partial differential equations at the same time, it can be hard to see the big picture. Okay, but the big picture of hydrodynamics is in fact quite simple. Ultimately, hydrodynamics is a macroscopic theory of things that cannot disappear, that is, they are conserved. Okay, so this is how we write conservation laws when we teach our students. The time derivative of some conserved density in the left-hand side is equal to minus the divergence of the conserved flux of that quantity in the right-hand side. So we write down these equations when we teach electromagnetism and we talk about the conservation of charge. We write down this equation in quantum mechanics when we talk about conservation of probability. Of course, we also write down this equation in the fluid dynamics when we teach fluid dynamics and talk about conservation of mass. But ultimately, this is how, in general, we write down conservation laws in physics. So the second ingredient that goes into hydrodynamics is what people call the constitutive relations. So what is the constitutive relations? So let's look at the conservation law that we have here. So let's say we are in 3 space dimensions. Then we have 4 unknown quantities. We don't know the density and we don't know the 3 components of this vector. So we have 1 equation and 4 unknowns. We cannot do much with it. Now, the biggest assumption of hydrodynamics is that this flux that sits in the right-hand side is that it is possible to express that flux as a function of the density in the left-hand side. And then you have the equation for the density that you can solve. Okay. So more generally, people do not necessarily work with densities. They introduce some useful quantities which they can measure, such as temperature or the velocity. and they express both the density in the left-hand side and the flux in the right-hand side as a functions of those useful quantities, which I call gamma here. And then you have the equations for those gammas that you can solve for. Okay, so here is a simple example. Let's take our density to be the density of energy, and let's take our useful quantity to be the temperature. Then in the left-hand side of the conservation law, you have energy density as a function of temperature. So that is something that you know from the equation of state. And then the constitutive relation expresses the flux of energy as a function of temperature. Now the flux is a vector, temperature is a scalar. The simplest way to make a vector out of a scalar is to take the gradient. So let me just take the gradient of temperature and stick in some coefficient out in front. So this coefficient is the heat conductivity. And then it is clear that when you look at deviations of temperature from thermal equilibrium, you get the diffusion equation, right? So from the left-hand side, you have one time derivative. So it's here. And in the right-hand side, you have two space derivatives, one from this divergence here and one from this gradients here. So you have two space derivatives in the right-hand side. So that is the diffusion equation. So that's how it arises in hydrodynamics. So here is the summary. You have two things. One is conservation laws. The other is the constitutive relations. And as we have seen, the constitutive relations can also involve derivatives of those useful quantities. So this fundamental procedure of how you think about hydrodynamics is the same, whether the fundamental constituents are quantum or classical, relativistic or not relativistic, normal fluid or superfluid, you have magnetic fields, no magnetic fields, chiral fluid, not chiral fluid. You don't even need to assume that the very concept of a particle or quasi-particle makes sense. As we know, the fundamental ingredients of matter are not necessarily particles, they're in general quantum fields, which may or may not behave like particles. If they don't behave like particles, hydrodynamics does not care, the procedure still works exactly the same. So for the constitutive relations, we have seen that you can have derivatives of those useful quantities. If you so wish, you can just throw away everything that involves the derivatives of those quantities. And if you do so, you get what people call perfect fluids, or the conservation equations, in this case are called the Euler equations. If by hand you throw away everything with two or more derivatives, and you only keep up to one derivative, you get what people call viscous fluids. The conservation equations in that case are called the Navier-Stokes equations. If you choose to throw away everything that has three or more derivatives, you get what people call second order fluids. The equations are the Burnett equations, and so on. So this is in general how hydrodynamics works at a basic level. Now, as physicists, well, we have to push our theory in various directions. We don't necessarily trust the equations. The equations are not sacred. We know that every theory in physics is wrong, or more precisely, every theory in physics is only approximately correct, limited by its domain of applicability. And whenever we write down any equations that attempt to describe physical phenomena, well, you have to answer, or you have to ask yourself, do the equations that we write down make physical sense? Can you improve those equations to capture more physics? And what kind of physics is beyond your equations? And my talk will have three parts, or three short stories, corresponding to each of those three questions. So that is the plan. So the first question, do hydrodynamic equations even make sense? So you may think it's such a weird question to ask. Of course they do. Hydrodynamics has been around for decades, centuries. If hydrodynamic equations didn't make sense, we surely would know about it, right? Well, let's not be so quick. So let's say you want to understand relativistic fluids. Let's say you're a student in subatomic physics or in astrophysics, and you want to learn about relativistic Navier-Stokes equations. Maybe you want to understand the core-gluon plasma produced in nuclear collisions, or maybe you want to understand the mergers of neutron stars. And as a student, you may wish to learn about those things from classic textbooks, right? And so there were the days, back in the day when people still used books, I remember them. As a student, I went through the Soviet School of Education, and every student in that School of Education was subject to the 10 volumes of the Holy Book. The Holy Book was called The Course of Theoretical Physics by Landau and Lifshitz. And volume 6 of that course was called Fluid Mechanics. And you can open the book on fluid mechanics, and there is a section on relativistic Navier-Stokes equations, and you can see what the equations are. And then I came to the West, to the US, to do my PhD. And then I realized there are other holy books besides Landau and Lifshitz. And I had a copy of Weinberg, Gravitation and Cosmology. And in Weinberg, there is also a section about relativistic hydrodynamics, and also there are some relativistic Navier-Stokes equations. And then you compare, then you realize those equations are different. Okay, Weinberg uses Eckart's version, and Landau and Lifshitz have their own. So what do? As a student, you are confused. But also as a graduate student, you are usually taught to shut up and calculate. Okay, well, let's shut up and calculate. And let's work out the simplest possible example that you can think of. Take fluid that is sitting there in global thermal equilibrium. Everything is uniform, no external forces, no external fields. And look at infinitesimal perturbations of that thermal equilibrium state. You can do this exercise very easily. And then you realize that both Landau-Lifshitz and Eckart's equations, they predict two things. Number one, they predict that thermal equilibrium does not exist. Or more precisely, this completely uniform equilibrium state without any external forces is unstable on a microscopic time scale, like microscopic, not macroscopic. And number two, the equations predict that things propagate faster than light. Okay, so I put down some references to Hisco and Lindblom, but these things were known well before. So, okay, it's a sad but true fact. The equations that you find in the classic textbooks, they make no physical sense. And this has led to the belief that the Navier-Stokes equations cannot be unified with Einstein's relativity and have to be abandoned in a relativistic setting. Other exotic theories have been proposed in the 70s to replace the Navier-Stokes. The most popular of those exotic theories goes by the name of Müller-Israel-Stewart. And the field has basically moved on, abandoning the Navier-Stokes. But as a student, you still have this nagging question. So why do the theories of Landau, Lifshitz, and Eckart, why do they differ in the first place? Okay, so the next slide is going to be very important. Okay, so please pay attention. Okay, so I'll give you a minute to read this slide. Okay. Okay, so this cartoon, well, it says basically measurement is important, temperature is important. So let's talk about temperature. So as we teach our students when we talk about thermal physics, statistical physics, temperature is something that is only unambiguously defined in equilibrium, and by definition, temperature is something that is measured by thermometer. Okay, so what I have here on the left are two boxes of identical stuff in identical equilibrium states. So this yellow thing or orange thing is my stuff. And then I have two thermometers that measure the temperature of my stuff. I have the red thermometer and the green thermometer. Thermometer is a little heat reservoir that is coupled to a gauge. So I have two gauges that show the same temperature in equilibrium if the two thermometers are correctly calibrated. Okay. Now, let me take the same two thermometers and stick them in identical non-equilibrium states. Now, in identical non-equilibrium states, these two thermometers will now show, in general, different temperatures. Now, why is that? Well, we know this very well from real-life experience. We have two thermometers that are made differently outside our window, and if the temperature drops very, very quickly, maybe one of them takes longer to react to temperature changes. Or maybe if the wind blows, the shape of this blob is different from the shape of this blob, and so the readings will be slightly different. These effects are very small. Of course, they're small, but they're important if you want to understand non-uniformities in the fluid, and this is precisely what Navier-Stokes equations is all about. It's about understanding non-uniformities in the fluid. So this tells you there is a certain degree of arbitrariness in what you mean by fluid temperature. And that is because the choice of thermometer that you choose to use is a convention. There is also the same arbitrariness in what you mean by fluid velocity. That is because your choice of velocimeter is a convention. Say, when you say velocity of the fluid, what does this mean? Is it the velocity according to which the energy flows, or is it the velocity according to which particle number flows, or is it velocity according to which the entropy flows, or is it some combination? They're all different things. There is no such thing as quote unquote the velocity of the fluid. And so Landau-Lifshitz version of Navier-Stokes, they use one convention, and Eckert version of Navier-Stokes, they use another convention. And of course, what happens is that there is simply no such thing as quote unquote the Navier-Stokes equations until you specify your arbitrarily chosen convention. Now, important, different conventions, they give rise to different mathematically inequivalent Navier-Stokes equations. Okay, it's not a typo. I do mean inequivalent. So the conventions have real consequences. Maybe not physical, but they do have mathematical consequences. And so this is because the Navier-Stokes equations only give you a crude approximation to a real fluid. The difference between these conventions is hidden in the crudeness of that approximation. Landau, Lifshitz, and Eckert, they adopt different conventions for Navier-Stokes, but both conventions are bad, and both conventions lead to nonsensical predictions. So what exactly is wrong with the classics? So one way to understand it is the following. So both Landau, Lifshitz, and Eckert define that temperature by the following relation. They say the exact non-equilibrium density of energy is equal to epsilon of t, where this function is given by the equilibrium equation of state. Okay, now let's think about it. So what is energy? So energy is something very, very fundamental in physics. If you have, basic principles such as, locality, energy density is something that is fundamental. It's part of like the definition of the very framework how we think about physics. Temperature, on the other hand, is just a proxy for energy. Temperature is not fundamental. If you wish, there is no temperature operator in quantum mechanics whose expectation value you take in some non-equilibrium state to get the answer. So what this equation means is that this means as the local energy density changes, the thermometer adjusts its temperature instantaneously, just like that. And if you think about this, if you work out the math, it will tell you that such thermometers that react instantaneously, they violate relativity and eventually lead to superluminal propagation in relativistic fluid dynamics. So, but then you can say, well, why don't you choose a thermometer or velocimeter that does not react instantaneously and respects relativity? So in other words, can you simply adopt a sensible convention? And the answer is yes, you can. This is something that people have started thinking about in the last couple of years. And with good conventions, indeed, you will find that the equilibrium state is stable, signals propagate slower than light, the equations are mathematically well posed, and can be consistently coupled to the Einstein's equations of general relativity. So in fact, good conventions do exist. So the bottom line of my first talk, of my first part, is that unifying Navier-Stokes with relativity was thought to be impossible for many decades. But I want to argue is that this is because people did not think carefully about those conventions. If you choose a physically sensible thermometer or velocimeter, then the Navier-Stokes indeed can be happily unified with relativity. So here, I usually say that we need to develop numerical codes and apply those equations to physical systems. But this slide is old because about 6 weeks ago, Franz Pretorius in Princeton and his student, they said, well, let's solve those equations. Let's write codes for them. And indeed, it's doable. They can be compared with other formulations of relativistic fluid dynamics, Muller, Israel, Stewart. So I'm not going to talk about this paper, but what I'm saying, it's work in progress. So the new formulations, both analytical and numerical, of fluid dynamics are being developed right now. But this also begs a question. So I phrased this question in a way that is slightly provocative, but I do think it's important to emphasize this. And so the way I argued is that sensible relativistic hydrodynamics it seems to require that its equations contain non-hydrodynamic parameters. So what are those non-hydrodynamic parameters? These are basically the parameters of your thermometer or your velocimeter. And every single formulation of relativistic fluid dynamics requires those parameters, be it Müller, Israel, Stewart, or this more recent one that I talked about, or other formulations that people have come up with. They all seem to require those non-hydrodynamic, non-measurable parameters. Now, if your equations contain those non-hydrodynamic parameters, this means your solutions will depend on those non-hydrodynamic parameters. And then you can ask yourself, if my solutions depend on those extra parameters that are not hydrodynamic, that cannot be measured, do your equations actually have predictive power? Okay, and it's not a trivial question. The answer may be yes, maybe no. So it's something to think about if you like formal questions. So my second story is, can you improve hydrodynamics? Are there limits to improving the hydrodynamic equations? So let's take a first look at the limitations of hydrodynamics. So macroscopic fluids, they're made of some microscopic constituents. Could be particles, could be fields, could be whatnot. So here is a cartoon of my microscopic constituents. And let's say these are particles. So it's a typical microscopic distance scale, like the distance between the particles, which I call little l. And when we work with macroscopic fluid dynamical equations, we solve for temperature, velocity, or particle number density as a function of space, and we have the distance scale on which our solutions change. This is what I call capital L. Maybe capital L is the wavelengths of the sound wave. Okay, and you would think that hydrodynamics probably should work if this capital L is much bigger than small l. Okay, if there are many particles that fit within one wavelength. In other words, when the derivative of this function is in some sense small. On the other hand, if you solve your fluid mechanical equations and you find solutions that look like this, that change with distance on the length scale that is comparable to this microscopic scale, then you say, well, hydrodynamics is probably not okay when these two length scales are comparable. In other words, when the derivatives are large. So this motivates this idea of trying to improve hydrodynamics by adding more and more derivatives. Okay, so remember I talked about these constitutive relations, how you express your densities and fluxes as functions of these useful quantities such as temperature or the fluid velocity. And so let me write down my constitutive relations as kind of a Taylor series, literally a Taylor series in quantities that have more and more derivatives. Okay, the superscript 0 means there are no derivatives of my useful quantities. Superscript 1 means there is one derivative. Superscript 2 means there are two derivatives, and so on. Okay, so no derivatives means perfect fluids. Of course, it's ironic. This is the most imperfect model of fluids. This is what people call perfect fluids. So these are fluids that cannot flow through a pipe. Sound propagates forever. Diffusion does not exist. If you add this one derivative, you get Navier-Stokes fluids. It's an improvement of the imperfect, quote unquote, perfect fluids. You introduce dissipation and restore common sense. Then you can try to improve it further to go to second order fluids and so on. Okay, so let's say we try to do this. Can you do this forever? Let's say you generate an infinite series in these gradients. Well, does the series converge or does it diverge? So converges like a series 1 over n squared gives you a finite answer. On the other hand, the series 1 over n does not give you an infinite n, does not give you a finite answer. So when you try to add more and more terms to improve your fluid mechanical equations, do you get something like this? Or do you get something like that? Okay, so if the series converges, then it tells you that hydrodynamics can be systematically improved to include more and more transport phenomena. And if the series diverges, then hydrodynamics is not really supposed to work. But then it seems to in practice. Then why does it work? Is hydrodynamics really a fluke? Okay, so how do we answer this question? Well, it's a very complicated question, so it's not clear how to answer in general. So, but let's look at very simple cases. Let's look at plane waves. You know, physics 101, we always teach about waves. So here's a plane wave, you know, complex exponential. For a simple plane wave, the derivatives, when you differentiate, this brings you a factor of I times the wave vector. K is the wave vector, inversely proportional to the wavelength. So in this case, the hydrodynamic expansion is an expansion in powers of the wave vector. Okay, so for example, when we look at sound waves, again, this is what we teach in elementary physics, how the frequency of the sound wave is related to the wave vector of the sound wave. It is given by power series in the wave vector. So the first term that we teach in very elementary physics has the speed of sound times k. So this is the just normal dispersion relation for the sound waves. There is a plus minus here because you can sound wave that can propagate in opposite directions. The second term comes from Navier-Stokes. Unlike the first term that comes from perfect fluids, the second one comes from Navier-Stokes. It is imaginary because it describes dissipation. This coefficient gamma is proportional to the viscosity. And then if you want to improve further, you will get k cubed, k to the 4, and so on. So you can ask this question, you know, do the series of these dispersion relations in your fluids, do they converge or do they diverge in hydrodynamics? And you say, okay, let's just compute those coefficients. Take, you know, water and compute all those coefficients, A, B, C, D, and so on. And, you know, actually, these are very hard to compute in practice. From first principle, it's virtually next to impossible to do so reliably. In general, even in kinetic theory, these computations are quite hard. So let me look at examples where these coefficients A, B, C, D, and so on can be examined. So the simple examples that I want to look at are the examples where you can do things analytically. So there are very neat examples in physics of fluids that can be studied analytically using the methods of so-called holography. So if you don't know what holography is, think about it as a mathematical trick. It's basically a mathematical trick to solve for the behavior of fluids that are morally speaking similar to the quark-gluon plasma produced in nuclear collisions. Okay, so in the simplest solvable examples, which you can do, well, we did this exercise of those solvable fluids. We found that this frequency, sound wave frequency, is indeed an analytic function of the wave vector, convergent for wave vectors smaller than some critical value, with, you know, some very nice answer, root of 2 and 2 pi, and temperature and Boltzmann constant, whatnot. So it gives you hope that hydrodynamics is improvable because the radius of convergence here is finite. But what I want to now talk about a little bit, I want to understand why. Why is there a critical wavelengths beyond which hydrodynamics stops making sense? Because it's really stark. It makes sense for wavelengths longer than that. It does not make sense for wavelengths shorter than that. So to understand why, so let's look at an example from basic math. Okay, so take a look at a function f is equal to 1 divided by 1 plus x squared. Okay, so here is a graph. Here is the graph of this function. Okay, so this function is perfectly smooth for all real x from minus infinity to infinity. Now, on the other hand, if you look at the Taylor series expansion of this function around the origin, well, it is given by the geometric series. And the Taylor series expansion of this function about the origin only converges when the absolute value of x is less than 1. Why is this? X is equal to 1 is here. The function is perfectly smooth. All derivatives exist. No singularities. What's wrong? Why does the Taylor series only converge when absolute value of x is less than 1? Okay, as we teach our students in complex analysis, we say, oh, you have to be smarter. You have to take x complex. If you take x complex, then you realize that this function has singularities in the plane of complex x when x is equal to plus minus I. And convergence really has to be determined by the circle whose radius is the distance to the nearest singularity in the complex plane. So this one here that limits the convergence of the Taylor series is really the absolute value of I. Okay, so going complex in this case is important. And the same thing actually happens with those dispersion relations. Frequency as a function of the wave vector, in those examples that we looked at, it is a smooth function at real wave vector. And to understand why those dispersion relations only converge for small wave vector, you must take your K complex. So let me talk about complex frequency and momentum a little bit. So how do these dispersion relations, frequency as a function of wave vector, or frequency as a function of momentum, or energy as a function of momentum, how do they come about? So they come about in simplest examples by solving some algebraic equation, some function of omega and k squared is equal to 0, where this function is determined by the equations that you're solving. Maybe you think about hydrodynamics, maybe Maxwell's equations in matter, maybe kinetic theory in more complicated examples. But basically, there is some function of omega and k squared. You set it to 0, and this is how you determine the dispersion, the relation between omega and k. So in this example of the diffusion equation that I talked about earlier, so the diffusion equation looks like this. It's very easy to see that this function capital F looks like minus omega minus dk squared. Why? Well, this is one time derivative from the plane wave, you get minus omega, and this two space derivative, when you differentiate the plane wave, like this, you get d times k squared. So this is a capital F for diffusion. If you think about sound, sound waves in viscous fluids, they look slightly more complicated, but not by much. The first two terms here is something that we teach in physics 101, how the frequency and the wave vector of a sound wave are related to each other. And then if you want to describe dissipation, there is also an imaginary term that comes from Navier-Stokes that gives you omega and k squared. And again, this gamma is proportional to the viscosity. Okay, so when we teach physics, we tell our students one of two things. So we write down some equations, say we talk about, waves propagating in, conducting media or whatever. And then we say, okay, we have this equation. So let's take omega to be a real number. And then in order to solve this equation, you can only solve this equation if k is complex. Okay, k as a function of omega will be complex. And then the imaginary part of k, you interpret as the damping length or the penetration depth for the wave to propagate inside the material. Okay. Another thing that we tell our students is, well, let's take k to be a real number. And then when you solve this equation, it turns out you can only solve this equation when omega as a function of k is in general complex. And then the imaginary part of omega, you will interpret as the relaxation time. Okay, so these are two things that we tell our students when we teach physics. Well, what if both are complex? Okay, this is not something that we normally talk about. So let me talk a little bit about what happens when both of them are complex. So how do I even visualize, function of two complex arguments? It's kind of hard to visualize. So to visualize what's happening here, I'm going to look at oscillation modes of fluids. So this is not an oscillation mode. These are not oscillation modes of water. So these are oscillation modes of those fluids that you can solve exactly using these methods of holography. So morally speaking, this is similar to the quark-gluon plasma in nuclear collisions. So the picture that you're looking at here, you're looking at the picture of the plane of complex frequency, real part of frequency, imaginary part of frequency. Frequency here is measured in units of temperature. And I take my wave vector to be a real number. So little q here is my wave vector in units of temperature. And then each dot in this plane corresponds to an oscillation mode of the fluid. If you want to be more formal, each dot in this plane corresponds to a pole of the exact retarded Green's function of the energy density. But basically, it is an oscillation mode of a fluid. These two dots, which are closest to the origin, they correspond to sound waves. There are two of them, this gold and the blue on either sides of the imaginary axis. There are two of them because of this plus minus. The waves can propagate in either direction. So the sound waves are macroscopic excitations. They can be well described by classical Navier-Stokes equations. And if you take the wave vector to 0, in other words, you look at longer and longer wavelengths, they will approach the origin, as all fluid mechanical modes should do. Now, these other dots that you see in the plane, these are microscopic oscillations. They have no classical interpretation. They're not described by hydrodynamics. They stay away from the origin as you look at longer and longer wavelengths. So think about this as basically, roughly speaking, modes corresponding to like molecular collisions. All right, so this is the picture that you have for a real value of the wave vector. Now I want to make my wave vector complex. Remember, Q is the wave vector measured in units of temperature. So what I'm going to do, I'm going to give my wave vector a phase, exponential I theta, and I'm going to change that phase from 0 to 2 pi. Okay, so here Q squared is equal to 1 in units of temperature, and I'm going to give it a phase, and I'm going to see what happens. Okay, so the picture that you're looking at right now is the picture when the phase is equal to 0. Now I'm going to change the phase from 0 all the way to 2 pi, and that is the picture when the phase is equal to 2 pi. So what happened? So these modes, they moved a little bit in the complex plane. They came back to where they started, except for these hydrodynamic modes, the blue and the gold. They swapped places, so it's easy to understand why that happened. But they basically remain sound modes. Now, if I look at longer and longer wavelengths, these two oscillation modes again will approach the origin. They will still describe, normal fluid dynamics. So this is what happened when my wave vector was 1 in units of temperature. Now let me take my wave vector to be 1.99 in units of temperature. Again, I'm going to give it a phase and change that phase from 0 to 2 pi. So this is the picture when the phase is equal to 0. Now the phase increases uniformly from 0 to 2 pi, and that is the picture when the phase is equal to 2 pi. Okay, so they move in a fancier way now. But again, what you will see is that this blue and the gold, they swap places, but they still remain sound waves. Now, if I take my wave vector to 0, or when I look at longer and longer wavelengths, they will still approach the origin here, as all hydrodynamic modes should. Okay, so the last picture I'm going to show is for my wave vector, not 1.99 in units of temperature, but for the wave vector, 2.01 in units of temperature. Okay, this is the picture when the phase is equal to 0. Now the phase increases uniformly from 0 to 2 pi, and that is the picture when the phase is equal to 2 pi. Okay, so what happened? So see what happened? This gold mode, or the orange mode, it used to be one of the sound waves. Now it became one of the non-classical modes. This green one was one of the non-classical modes. Now it becomes one of the sound waves. If I now take my wave vector to 0, or the wavelengths to infinity, it's the blue and the green that will behave like sound waves. It is the blue and the green that will obey the Navier-Stokes. And what used to obey Navier-Stokes, this orange one, will not obey Navier-Stokes. Okay, so what you see is that the wave vector became, after the phase of the wave vector rotated, the hydrodynamic mode became a microscopic mode, and a microscopic mode became a macroscopic mode. So the picture that you're looking at here is the picture, is the same information that you saw in the animations. The lines here, they show the paths that are traced out by those dots as the phase changes from 0 to 2 pi. When the wave vector is 1.99 on the left, when it is 2.01 on the right. And what you see here is that the shape of those trajectories that are traced out by my modes, the shape is different. Okay, so what has happened? Of course, you can already guess what has happened. When q squared is equal to exactly 2, you have a collision of modes. So the modes collide, and the topology of those trajectories changes. So what you are looking at here, you're looking at level crossing. But it's not level crossing in quantum mechanics that we normally discuss. This is level crossing in a macroscopic dissipative system, when a classical hydrodynamic excitation becomes a non-classical excitation. And in order to see this exchange, you need to take the wave vector and frequency to be complex. So it is this collision of singularities that actually determines for you the convergence of the hydrodynamic expansion, and this is something that gives you the critical wavelengths for sound. There is actually more to complex momentum. I will only mention this very briefly, but I cannot resist because it appears so cool. This is the relationship about complex momentum and chaos. So what is chaos? Well, it kind of depends on who you're talking to. Different people mean different things. But roughly speaking, chaos is about how microscopics gives rise to macroscopics. Okay, so in classical mechanics, one way to characterize chaos is through the Lyapunov exponent that describes the divergence of phase space trajectories as time goes on. And people have argued that there exists a quantum analog of this classical Lyapunov exponents. And the quantum analog basically has to come from the expectation value of the commutator squared. In this case, Q and P are position and momentum operators, but you can look at other more general operators. And in many systems, when you look at the expectation values of the commutator squared, it will grow exponentially. And this exponent lambda is what people normally identify with the quantum version of the Lyapunov exponent. So far, this has nothing to do with hydrodynamics, except people started to dig deeper for those models that I was talking about, those holographic models. And then they figured out that if you do this very silly looking thing, that is, you take a plane wave, exponential minus r omega t plus ikx, and you take omega to be purely imaginary, I times lambda, and k to be purely imaginary, I lambda over v. Your plane wave becomes something that looks like this. And it turns out that this number here will be the Lyapunov exponent if you trace out the sound wave dispersion relation at complex frequency and complex wavelengths. So what this tells you basically is that if you look at the dispersion relation of sound when the frequency and the wave vector are complex, that dispersion relation seems to know something about the quantum Lyapunov exponent. Okay, so why is this? How general this is? These are all kind of open questions. It's clear it's not completely universally general, but in many models that people have studied, that seems to be the case. So the bottom line of my second story is this: in many solvable examples, classical macroscopic excitations and non-classical microscopic excitations, they're merely different branches of the same multi-valued complex function. And also in many solvable examples, classical hydrodynamics at complex momentum, it seems to know about quantum Lyapunov exponent. So basically, going complex for hydrodynamics can tell you about things that you did not know about before. So my last story is basically this. So why everything I said so far is wrong. All right, so let's take a second look at the limitations of hydrodynamics. Okay. So, okay, macroscopic stuff is made out of microscopic stuff. So if you think about, the relations between microscopics and macroscopics, let's think about quantum mechanics. In a quantum vacuum, virtual particles are constantly produced and absorbed due to quantum fluctuations. Similarly, in a macroscopic state, virtual sound waves are constantly produced and absorbed due to statistical fluctuations. And the sound waves will backreact on the macroscopic physics because hydrodynamics is a nonlinear theory and waves interact. So what I have here is a cartoon of my big macroscopic sound wave shown in thick blue line, and I have a statistical fluctuation here that generates sound waves shown by thin lines. And this statistically generated sound waves will backreact on the big sound wave, which you thought was your sound wave from classical Navier-Stokes. Is this backreaction relevant? Well, in quantum mechanics surely is. The backreaction of quantum fluctuations is responsible for most of the mass of the matter we see in the universe. This is, of course, what gave rise to the Physics Nobel Prize in 2004 to Gross, Politzer, and Wilczek. Now, the backreaction of statistical fluctuations is usually not so dramatic, but it does modify Navier-Stokes equations near liquid gas critical points and in 2 space dimensions. Actually, in 1, it's even worse. So should you care? Depends on the questions that you ask. The relationship of hydrodynamics to microscopic physics is like classical mechanics to quantum mechanics. Now, if you look at correlations, so that is when classical versus quantum predictions can differ quite dramatically. And similarly, if you're interested in macroscopic long distance, long time correlations, then classical hydrodynamic equations which ignore the backreaction, they can lead to dramatically wrong predictions. This was discovered many years ago in the early days of molecular dynamics in the simulations of billiard balls. Those people said, okay, let's look at a gas of billiard balls, billiard discs, let's simulate them, see how they move. Does the macroscopic physics look like Navier-Stokes when you look at correlations? It may not. Well, they found it did not. So what will this lead to? Okay, so to understand those effects, hydrodynamics is not going to be differential equations. Power series like this that I talked about earlier, this will not work. Quantum Lyapunov exponents and connections to hydrodynamics, this will not work. Normally, you think that transport coefficients such as the viscosity will determine the long distance correlations. That will not work. And in fact, this incompleteness of classical hydrodynamics has been well known in statistical physics going back to 1970s. So let me talk a little bit, spend maybe the next 5 minutes or so, and then I'll finish to talk a little to talk about this in slightly more detail, in some more detail. Okay, so let's look at viscosity. So what is viscosity? The physics of viscosity is the transfer of momentum between different layers of fluid. So what I have here on the left is a picture when the fluid moves from right to left. So these yellow arrows represent the fluid. So the fluid moves quickly on the bottom, it moves slowly on top. And these blue lines here, they represent particles that can jump between different layers of the fluid. So if this particle jumps from a fast layer, it jumps to a slow layer, it can transfer momentum from a fast layer to the slow layer. It can speed up this fast layer. And so in a gas, in fact, the viscosity is proportional to this distance that the particles jump. So this is what people call the mean free path, the average distance traveled by the particles, and the viscosity is also proportional to the particle density and the mean velocity of those particles. Now, in fact, if you think about what gives rise to dissipation, it's not just the viscosity itself. Say for sound waves, what gives rise to dissipation is the so-called kinematic viscosity. It's viscosity divided by the by the mass density. In relativistic fluids, mass density is not necessarily, a useful concept. So it's much better to think about the density of entropy. So it's the viscosity divided by the density of entropy that tells you about the dissipation of sound waves. It's basically a quantity that is dimensionless in natural units. So think about it this way. So viscosity divided by the density of entropy can be represented like this. In a gas, you write the mass density as mass of one particle times the number density, mean velocity times the mean free path. Viscosity, density of entropy is roughly same as density of particles. So you write this as average momentum of your particle times the mean free path. And of course, this is a classical gas. So in a classical gas, this has to be much larger than h bar. But this also tells you that viscosity over the density of entropy has natural units of the Planck's constant. And so how far this number is from Planck's constant basically tells you whether your fluid is classical or quantum. So normally when you have weakly interacting constituents, the viscosity over entropy ratio is going to be a number that is much, much larger than h bar. When the constituents start interacting stronger, okay, it may be larger than h bar, but may become comparable to h bar. When the constituents of your matter interact very strongly, you have a quantum liquid. This may become comparable to h bar, and it's a very hard problem to normally a very hard problem to study. You cannot use Boltzmann equation, for example, for those systems. But even though in this regime you cannot use Boltzmann equation, you can use these other methods of holography that I was talking about. It's basically, again, as I said, as a mathematical trick. The more precisely how this mathematical trick works, it's a duality relation between fluids of strongly interacting constituents and black holes. This may sound like magic. It's a little bit like magic, but the math works out. So it's something that people have been working on for many, many years. So in particular, this duality says that if you want to understand waves in fluids, such as sound waves, you can extract information about waves in fluids from certain properties of gravitational waves. This is how this works. And in fact, for all such fluids where this duality works, one finds that the viscosity over the density of entropy is h bar divided by 4 pi. So it's a precise answer. And in practical terms, this means you're looking at near perfect fluidity. In practical terms, this number is very, very small. It's actually smaller than the viscosity of superfluid helium. It's not too far from the viscosity of the quark-gluon plasma. There's lots of work about that, but that's not what I want to talk about. So what I talk about is something slightly different. Remember how I talked about that momentum can be transferred by particles? Momentum can also be transferred by collective excitations. So here is the same picture that I had before. And I have a gas of sound waves that are statistically generated. So the thin blue lines are now my sound waves, not particles. And the mean free path of the sound wave is inversely proportional to the viscosity. And of course, it's also inversely proportional to k squared. So this follows from this relation for the frequency of sound that I wrote down earlier. But basically, you know that marine mammals, whales, they use very low frequency waves to communicate. They don't use high frequency screams. So why do they use low frequency waves? Because low frequencies propagate further than high frequencies, right? And so this is essentially reflected in this formula here. Now, if you look at the contribution of the sound waves to viscosity, well, you integrate over all possible wave vectors. So you have to sum over all possible mean free paths. And when you look at this, then, okay, so you get some contribution to the viscosity that is inversely proportional to the mean free path in 3 dimensions. And this integral is divergent at long distance in 2 space dimensions, which means that if you want to understand the back reaction of sound waves, well, in 2 space dimensions, your Navier-Stokes may not be quite right. All right. So I will finish maybe in a couple of minutes. So I'm very close to the end. So how do you describe these effects? So there's some quote unquote old-fashioned way to describe these effects is you treat hydrodynamics like Brownian motion. The way you do it is you add some kind of noises. Just like in the Langevin equation, you add a random force to describe the Brownian motion. So here you add random flux. to describe the effects of these back reactions. And so you get so-called stochastic differential equations with Gaussian noises. But there is actually a modern way to look at those back reaction effects, and that is to treat hydrodynamics like field theory, similar to what people do in the standard model of particle physics. So you will have an action in terms of cleverly chosen variables. You will have Euler-Lagrange equations that are the same as the conservation laws. This is slightly different from what we normally do in classical mechanics. When we teach classical mechanics, we say, okay, these are the Euler-Lagrange classical equations, and then they imply the conservation laws. But here you want to engineer it in such a way that the Euler-Lagrange equations are the conservation laws, energy, momentum, particle number, whatnot. You want to, if you are in equilibrium, you want to impose fluctuation dissipation theorem. You can impose this as a symmetry of your Lagrangian or of your action. If you want to do this with the path integral, like similarly to what people do in quantum mechanics, your time has to run forward and then backward. It's not hard to understand why. This is because when you look at the Heisenberg time evolution in quantum mechanics, the time dependence of operators is determined by the time evolution operator and the conjugate, which describes forward and backward time evolution. But basically, the point is you can convert hydrodynamics into some kind of field theory similar to the standard model. So the bottom line for my final story is that if you want to understand correlations at very, very small frequency or late times, long distances, then using classical hydrodynamics is actually not reliable because of those back reactions. So the deviations from classical partial differential equations are more pronounced at small viscosity. Short time statistical fluctuations will give rise to late time correlations that are determined by the viscosity. But more generally, if you want to understand late time correlations, you will need more information than what is contained in the classical equations of hydrodynamics, even taking into account to all orders in this derivative expansion. You need extra things like stochastic transport coefficients that I can talk about later if you ask me. So where does this leave us with all of that? So for many years, I had a dream of a grand unified theory of hydrodynamics, which is sort of like the grand unified theory of particle physics. And the difference is grand unified theory of particle physics talks about particle physics. And what about particle physics? Particle physics is basically about infinitesimal perturbations on top of the vacuum state. Okay. But what if you want perturbations not on top of a vacuum state, but on top of a macroscopic state with finite density of energy? Then you need a grand unified theory of hydrodynamics. So, it would be nice to have a grand unified theory of hydrodynamics that applies to different kinds of fluids, ensures that the equations are sensible in the sense that I talked about at the beginning of the talk, allows for systematic improvements, correctly predicts macroscopic correlations, connects with quantum chaos, and most importantly, is experimentally verified. And it seems that this requires developing new kinds of field theories of the type that I briefly mentioned. This is work in progress that many people are actively working on right now. So I want to finish with an encouragement for students. Okay, so as a student, one often tends to think that all interesting questions in physics have already been answered many years ago by the great. Hydrodynamics is an ancient field by modern standards. And as I try to convince you, people are still trying to figure out some very basic questions even now. So if, as a student, you work in a field that is less than 200 years old, do not lose hope. There are surely many fundamental things left for you to discover. Thank you for your attention. Thanks.
Well, thank you very much for this very beautiful talk. So we have time for some questions. So if you have a question, please raise your hand and turn on your mic. So I can see that Pierre has a question. So
yes,
Go ahead.
Gaspar from ULB. I would probably have many comments on the different aspects of your talk, but I would like to point out that hydrodynamics and the long time tails in hydrodynamics is a very well-known subject. There are very good books and papers. And so indeed, the dispersion relations are not analytic. So we need to include branch cuts in the complex plane. And this is very well known. So you can go from one Riemann sheet to another Riemann sheet and meet poles, etc. There is no problem actually. You are giving the picture that all this should be going to the garbage, but you are not taking into account that there has been many works with very subtle aspects of hydrodynamics. In particular, in one dimension, Henk van Beieren has shown that the equations are actually within the universality class of the KPZ model, and this can be done. There is no problem with that.
Yes, I completely agree with everything that you said. And I, of course, am well aware of that vast body of literature in statistical physics and corrections to hydrodynamics. And I maybe it didn't come out right in the talk, but I under no circumstance I want to argue that all of that should be going in the garbage. In fact, it should not. In fact, what I want to argue is quite the opposite. So I want to argue that these effects are extremely important. And these effects need to be taken into account. And so the new thing that I wanted to emphasize is that on top of that vast body of literature that has existed since 1970s, including the KPZ, of course, universality class, the renormalization group in two space dimensions, and other things, there exists a field theoretic way to treat those effects that is more general than what people have done in the 1970s, that encompasses those things, but allows to do more than what people have done earlier. So yeah, under no circumstances. So when I'm saying that. When I'm putting like crosses here, this just says that those effects, they simply invalidate hydrodynamics as a classical equations. Of course, hydrodynamics is not classical anymore. You need to take into account the effects of fluctuations, right? It's not classical physics. You need to take into account path integral, stochasticity, whatnot. No, you don't agree? Tell me.
No. In three dimensions, the standard Navier-Stokes equation, for instance, you mentioned the Burnett equation with the correction, the next correction, the dispersion relation. If you look at the next term, it goes like k to the power of 5 over 2. So it's non-analytic.
Yep.
So, but we can use the Navier-Stokes equation. There is no problem in using the Navier-Stokes equation as a partial differential equation. Although if we go on different scales, we may indeed meet the effects of
yes, I completely agree. And so I'm saying, so we're not talking about different things. I'm saying exactly the same things as you are saying. Right. So when I say hydrodynamics cannot be understood as differential equation, so let's look at that correction that you looked at. This means that the correction is more important than the Burnett equations in 3 space dimensions, right? And so this is the content of that little cross, that you cannot use classical Burnett equations to understand those corrections, right? So this is what I meant when I put a cross here, right? Okay. And so the same thing is that what I meant when I put a cross here. I meant precisely the same thing that you mentioned, is that there is going to be branch cuts. There's going to be branch cuts because of the effects that you said. And so there will be non-analyticities here. And so there's a cross here because this does not work and those branch cuts have to be included. That's exactly, that's right. So, and the same thing here. Now, maybe one thing that I wanted to mention about this, this level crossings and non-analyticities is that these branch cuts that I talked about here, this level crossing. So this is something that exists even without taking into account these effects that Pierre just mentioned. Okay, so this is purely in the context of a classical theory that does not have any of these long time tails, does not have any of the branch cuts. Because the branch cuts that Pierre mentioned are the branch cuts that would go all the way to the origin or close to the origin here. Whereas these level crossings here, they happen away from the origin, they happen away from the hydrodynamic regime, where you have the transition between the macroscopic mode and the microscopic mode. Of course, the complete theory has to take into account both kinds of branch cuts. It has to take into account this level crossing, and the type of effects that that Pierre mentioned. Yeah.
Okay. Other questions? Maybe I have one. No, Luca, please go ahead. Turn on your mic, please.
Hello, hi. Can you hear me?
Yes.
Hi. Hello, Pavel. Thanks for the talk. Just one question. It's just a curiosity. What about turbulence, Reynolds number?
Yeah, well, excellent question. So turbulence is, of course, like the prime example of a non-equilibrium system. And, you know, of course, the field theoretic approaches to turbulence and diagrammatic techniques in application to turbulence have been well known since 1960s, the work by Wild. You know, these field theoretic methods that you know, I briefly mentioned here treat hydrodynamics as a field something similar to the standard model of particle physics. This really hasn't even scratched the surface of turbulence. This is, I think, where that field will go eventually, but it has just, you know, these developments have started very recently. You know, so like one prominent physicist told me that, you know, he said, Pavel, physics gets reinvented every 25 years. And, you know, new generation comes and, you know, they start looking at this old problem with the angle that they like, and so on. And so there is, you know, a great degree of truth to that. So I think this fancy Schwinger-Keldysh effective field theories that people have started constructing now, they will be applied to turbulence, not now, but in the next, I expect, you know, 5-10 years. Another question that, you know, related to turbulence is maybe it's about relativistic fluids that I talked about earlier, is that, you know, does hydrodynamics have predictive power? Because I mentioned that equations, relativistic fluid mechanical equations, they do contain non-hydrodynamic parameters. This is true for Israel Stewart, you know, it's true for every single setting. Now, what are these non-hydrodynamic parameters? These non-hydrodynamic parameters, this is basically described for you short distance, short time physics. So it's not something that is within the validity regime of hydrodynamics. So you don't trust it, but it's something that seems to be needed to make your equations hyperbolic. Okay, so on one hand, you need it to make your equations hyperbolic. On the other hand, you don't trust it. So speaking of turbulence, so there may be a difference now in terms of the turbulent cascade that goes in different directions in 2 space dimensions and in 3 space dimensions. So in this case, the physics that contaminates your fluid mechanical equations is the short distance physics. So if your cascade goes from long distance to short distance, where it is dissipated by the viscosity, then maybe you can argue that it does not matter. Does not matter because whatever these things that you don't trust, viscosity kills them before they become problematic. On the other hand, if you're in two space dimensions where the energy cascade goes from short distance to long distance, maybe this will be a problem because short distance effects, they can grow to long distance. But really, I don't have much, to be honest, I don't have much intelligent to say about this, except that maybe the types of solutions that hydrodynamics that relativistic fluid mechanics describes, whether you should trust them or not depends on the solution. Some solution you maybe can trust, and other solutions you will not trust.
Yeah, maybe one of the problems is also that I'm just checking whether you agree. It's not to, but to overstate anything, is that probably in the trick that we use, which is holography, is not easy to find out some holographic setup with turbulent fluids. Would you agree on this?
Right. There has been some works by the MIT group, a few years back. What they looked at, from what I remember, they looked at the decaying turbulence, not the driven turbulence. Yeah, it's tricky. And even in holography, since you mentioned holography, the very question, do the equations that people currently use in relativistic fluid dynamics, do they agree with the fundamental, holographic results? This question has been somewhat underexplored. Okay, because in these holographic methods, they allow you to extract the full dynamics of energy and momentum and baryon density, regardless of any hydrodynamic assumption. Regardless, it's like a microscopic exact calculation almost, except it's numerical. Now, when you look at that nonlinear evolution of the exact nonlinear microscopic evolution, does that agree with what people use in fluid dynamics? And this has been explored, but only a little bit. There's surely a lot more work needs to be done in that regard to say, do you really trust relativistic hydro? In fact, actually unrelated to that, I'll just make one brief comment. Last month, there was a paper by Georges Neroni in France, where they looked at violations of causality in relativistic simulations of nuclear collision. This is unrelated to holography, but then they said, okay, let's take state-of-the-art codes that people use to simulate the quark-gluon plasma. And they use Israel-Stewart equations, which may or may not be hyperbolic, under certain assumptions. And then they check those assumptions. And they, lo and behold, they have in this part of the quark-gluon plasma of the simulation causality is violated, and this part is not violated. Okay, so what do you do about it? I guess there's definitely work to be done, along those lines. Yeah.
Thank you very much. Thanks.
Okay, thank you. Any other question? Well, I don't see any. There is one question by Joseph Lemaire. So please go ahead and turn on your mic, please. We cannot hear you.
I just have a simple question. The theory of Chapman-Enskog has been accepted for so many years. And as at least when collisions in the gas are high enough, would you say that the hydrodynamics be based on the Chapman-Enskog theory is wrong?
No, I would not say it's wrong. But I would say that okay. So based on what I know, well, okay. So it depends on what we mean by hydrodynamics. So let's say we take into account you know, those effects that Pierre mentioned. You know, the long-term tails and the corrections, and you know, the sub you know, non-analyticities, what happens in the at higher orders and the derivative expansion. Would you consider that to be, you know, part of hydrodynamics? I would. I would say this is the physics of correlations at long distances and you know, late times. So I would call that to be part of hydrodynamics. I don't think the Chapman-Enskog expansion captures those effects. So from that point of view, I would say that kinetic theory description is incomplete. On the other hand, kinetic theory can capture, you know, more things that are invisible, you know, to those methods that I talked about. So maybe what I can do is I can draw a cartoon here. So the cartoon that I want to draw will look like this. So this horizontal axis is what, roughly speaking, I call G, is the interaction strength of the constituents in the fluid, whether the constituents are particle-like or field-like, particles exist or do not exist. So over here, I will call something like a gas, something that is describable by kinetic theory. And on this part of the diagram, I would call maybe theories without particles. So maybe strongly interacting quark-gluon plasma at not too high temperatures will be in here. Cold atomic gases that sit at the tuned at the point of the BCS-BSC crossover would be here. Strongly interacting quantum critical points would be here. Holography would be here, and then there is something in between. Now on this axis, I put you know, the frequency. You know, frequency of excitations that your fluids have. Now over here, you know, there's frequency corresponding to particle collisions. Then there are different, you know, molecular degrees of freedom and whatnot. So the regime of kinetic theory is this regime. The regime of these holographic models is this regime. The regime that I want to describe using those effective theories and also the effects that Pierre talked about is this regime right here. Okay, so there is overlap in these effective theories that I talked about. There's an overlap with kinetic theory. There is overlap with those holographic models. But there is also supposedly a validity regime of the theory at intermediate, you know, interaction strengths that is not captured by the effective theory. It's not captured by the holographic models, but is captured by. So this is the regime of indeed low. Or maybe I shouldn't be putting it here. This you know, the shaded regime here is the regime of low frequencies and small wave vectors. So I would never say that Chapman-Enskog is wrong, but I would say Chapman-Enskog cannot give you access to that shaded regime here.
Okay, thank you.
Okay, I guess that's a nice way to conclude. It gives a great picture. So I would suggest that we thank our speaker again.
Yeah.
Very good. Excellent talk. Thank you very much. And well, it's a pity you are not here with us in Brussels. We could have a beer together, but that would be for next time when we are back to normal life. So thank you.
Yes, I'd like to visit. Thank you. Thank you.
Thank you. And bye-bye.
All right. Bye-bye. Thanks.